Welcome to Brain Vision.
To find the velocity of a cat at 4 seconds and 7 seconds, we simply read the graph on page 60, figure E2:30. So for part A, looking at the graph, we see that the velocity at t equals 4 seconds is equal to 3 meters per second. And the velocity of the cat at t equals 7 seconds is equal to negative 1 meters per second. And let's add another significant figure here since the time is given to 2 sig figs. Okay, so that's part A, easy enough. For part B, let me just label this part A. Part B, we're asked to find the cat's acceleration at 3 different times, at 3 seconds, 6 seconds, and 7 seconds. Now, since the velocity is changing at a constant rate, see we have a straight line on the graph, it's not curving. That means the velocity is changing at a constant rate, and so the acceleration is going to be the same everywhere. So all we need to do is just calculate the change in velocity over any interval, and it should give us the same answer as if we used any other interval at any other time. So let's go from t equals 0 to t equals 6. So we know that acceleration is defined as the final velocity minus the initial velocity over time. Let's say that our time interval is 6 seconds. We'll go from 0 to 6. And let's call our final velocity 0. Oh, and it looks like these are in centimeters per second. I didn't notice that, so let me change. And then the initial velocity is going to be equal to 8 centimeters per second. Plugging everything in, you get 8 over 6, which is equal to 4/3 centimeters per second squared. Oh, and it should be negative since the velocity is decreasing with time. And this is going to be the acceleration at t equals 3, t equals 6, t equals 7, because again, the velocity is changing at a constant rate. So the acceleration is constant. Okay. Now, moving on to part C, we want to find the distance the cat moves during the first 4.5 seconds. Well, one formula we could use is the change in distance as a function of time, but I think actually the easiest way to go about this would just be to use the normal position as a function of time equation. So we have x final is equal to x initial plus v initial times t plus a over 2 times t squared. We can call our initial position 0. So, and our initial velocity, since we're starting at 0, is going to be 8 centimeters per second times 4.5 seconds plus negative 4/3 divided by 2. That's the same as negative 4/6, which is the same as negative 2/3. Oh, whoops. sorry, let's put that back. So we had 8 centimeters per second times 4.5 seconds minus 2/3 times 4.5 squared. 23rd power just squared. Now entering this into a calculator. You get 22.5 centimeters. Now repeating this over a longer interval, over the first 7.5 seconds, it's the exact same, except now we plug in 7.5 instead of 4.5. So we have 7.5 times 2 divided by 3. Ooh, and we also get that during the first 7.5 seconds, we get the same answer, the same distance traveled as distance traveled during the first 4.5 seconds. Now, this may seem a little strange, but if we look at this graph again, we can see why this is the case. We notice that the velocity is constantly decreasing until it actually goes negative. So once we go past 6 seconds, the cat actually changes direction. And so that's why once we go to 7.5 seconds, we end up at the same place we were at 4.5 seconds because where the negative velocity just gets us back to that spot. Okay, now for the last part of this, part D, we want to sketch graphs of the acceleration and position as functions of time. So the acceleration is easy. Whoops, I cannot draw straight lines. There we go, that's better. So the acceleration is just going to be a straight line since it's constant. And actually, it should be negative since we said it was negative 4/3. So if this axis is the acceleration, and this is time, and if right here is negative 4/3 centimeters per second squared, call that right here, and our acceleration is just a straight line. Now, position is a little trickier, but it's not too bad. Position should increase until it gets to 6, and then start decreasing again once the velocity goes negative. So if we do position as a function of time, this is our x, this is our t. Now notice the position function is a quadratic. This means that the position is going to be the shape of a parabola. What I mean by this is that this equation, quadratic. Quadratic looks like a parabola. Oops, this should be a plus. Oh, whoops. Anyways, you get the point. So our position should increase parabolically. Let me try that again. Till it gets to t equals 6 seconds, upon which it just starts decreasing again. Let me see if I can draw that a little smoother. for this right here is 6 seconds.